Hi friends, today we shall be discussing in detail about various sorting algorithms. Sorting, as we know, is the process of rearranging a sequence of objects so as to put them in some logical order. The aim is to put unordered information in an ordered form such as alphabetical order, order according to name, ID, age, department, etc., ascending or descending order. In the early days of computing, around 25% of all computing cycles were spent on sorting. Even now, it is estimated that 20% of computing time is spent on sorting. If that fraction is lower today, one likely reason is that sorting algorithms are relatively efficient, not that sorting has diminished in relative importance. In everyday life, we have numerous examples of sorting. People arrange their cards while playing, or during exercise, persons are organized on their heights, or a list of students could be sorted in ascending order by roll number, name, date of birth, or on descending order on marks. Sorting algorithms are a standard topic in introductory courses in computer science, not only because sorting itself is an important issue, but also because it is particularly suited to demonstrate that there can be several very different solutions to the same problem, and that it can be useful and instructive to compare these alternative approaches. Sorting algorithms provide an introduction to a variety of core algorithm concepts such as big O notation, divide and conquer algorithms, data structures, best, worst and average case analysis, time space trade-offs and lower bounds. Sorting plays a major role in commercial data processing and in modern scientific computing. Applications abound in transaction processing, optimization, astrophysics, molecular dynamics, linguistics, weather prediction and many other fields. We shall have a detailed look on the sorting applications in next section. Indeed, a sorting algorithm, Quicksort, was named as one of the top 10 algorithms for science and engineering of the 20th century. So, the problem of finding efficient sorting algorithm is immensely important. Unfortunately, no single sorting technique is the best for all initial orderings and sizes of the list being sorted. Even though more than 100 sorting algorithms and their variants have been developed, but even today sorting algorithms are still being optimized or new ones are being invented. Applications. The practical applications of sorting are far too numerous to be listed, but still we state some of the common applications. Words in a dictionary are sorted. Files in a directory can be sorted on name, date, type or size. The index of a book is sorted. The email or phone calls are sorted by time or origin. The mobile address book is sorted by name. Music libraries are organized by album or artist. Credit card companies sort millions or even billions of transactions by date or amount. Search engines display the results sorted on page rank. Universities sort student records by names, roll numbers, age, marks, etc. Government organizations, financial institutions and commercial enterprises organize most of the information by sorting it. Whether the information is accounts to be sorted by name or number, transactions to be sorted by date or amount, mail to be sorted by postal code or address, files to be sorted by name or date, or whatever processing, such data is sure to involve a sorting algorithm somewhere along the way. Another reason why sorting is so important that once a set of items is sorted, many of the problems become easy. Some of the common indirect applications of sorting are searching. Sorting makes it possible to search a particular data item in a collection quickly by applying the binary search technique. We are using it every time in real life when we look up a word in a dictionary. Imagine searching for a word in a 1000-page dictionary which is not sorted alphabetically, and you will appreciate the importance of sorted data for lightning search. As an example, we have two small lists, one sorted and another unsorted, and try searching for a word in both the lists. Some other indirect applications of sorting are median and selection. What is the kth largest item in a set? What is the median of a set of values? All this can be very quickly answered by sorting the keys. The keys are placed in sorted order in an array. The kth largest can be found in constant time by simply looking in the kth position of the array, as shown in the following slide. The median can also be quickly found by looking at the middle element in the sorted list. Duplicates. Are there any duplicate keys in an array of comparable objects? How many distinct keys are there in an array? Which value appears most frequently? With sorting, one can answer these questions in linear arithmetic time. First, sort the array, then make a pass through the sorted array, taking note of duplicate values that appear consecutively in the ordered array. Do a linear scan to measure the length of all adjacent runs to find the most frequent term. Convex hulls. Given n points in 2 dimensions, find the smallest area polygon which contains them all. The convex hull is like a rubber band stretched over the points. Convex hulls are the most important building blocks for more sophisticated geometric algorithms. Once you have the points sorted by x coordinate, they can be inserted from left to right into the hull, since the rightmost point is always on the boundary. Without sorting the points, we would have to check whether the point is inside or outside the current hull. Painter's algorithm. The Painter's algorithm is one of the simplest solution to the visibility problem in 3D computer graphics. The algorithm sorts all the objects in a scene by their depth and then paints them in this order, farthest to the closest. As seen in following slide, the distant mountains are painted first, followed by the closer meadows. Finally, the closest objects in this scene, the trees, are painted. Huffman coding. Huffman coding is one of the earliest data compression algorithm based on the frequency of occurrence of a data item. The principle is to use a lower number of bits to encode the data that occurs more frequently. To design the best possible code, the first and most important step is to sort the data items in order of frequency or probability of occurrence. Also, human beings like looking at ordered sets of data, and as such, sorting can be useful at the level of presentation. Classification of sorting algorithms. Since the early beginning of computing, the sorting problem has attracted many researchers, perhaps due to the complexity of solving it efficiently. Many researchers considered sorting as a solved problem. Even so, useful new sorting algorithms such as library sort are still being invented. As already mentioned before, more than 100 sorting algorithms and their variants have been developed. Each algorithm underpins a beautiful idea. It is interesting to see how people think differently and come up with so many solutions for the same problem. Every algorithm has its own beauty, its own flavor and its own idea. The algorithm differs like: one is fast, one is simple, one is general, one is flexible, one is slow, one is easily implementable, one works best for large data size, one works best for numbers in a file, One works best for almost sorted numbers and many more. A list of 40 popular sorting algorithms is shown in the following slide. We can classify sorting algorithms by several different criteria. Computational complexity. Sorting algorithms are often divided into two complexity classes: simple to understand algorithms such as bubble or selection sort, whose complexity class is order n square, and more complicated algorithms such as merge sort and quick sort, whose complexity class is order n log n. Algorithms differ in the constant that appears in front of n square or n log n. Furthermore, some sorting algorithms are more sensitive to the nature of the input than others. Quicksort, for example, requires order n log n time in average case, but requires order n square time in the worst case. Stability. Stable sorting algorithms maintain the relative order of records with equal keys. If all keys are different, then this distinction does not make any sense. But if they are equal keys, then a sorting algorithm is stable if whenever there are two records R and S with the same key and with R appearing before S in the original list, R will appear before S in the sorted list. But why should this be important? Well, the question of stability in a sorting algorithm arises when we wish to sort the same data more than once according to different keys. Sometimes data items have multiple keys, and we may very well want to sort such data according to more than one of the keys. The trouble is, if we sort the same data according to one key and then according to a second key, the second key may destroy the ordering achieved by the first sort. But this will not happen if our second sort is a stable sort. Suppose, for example, that we have a file containing a list of students who are enrolled in several different lab sections. Say Dravid is in lab A, Aman is in lab B, Kusum is in lab A, Eric is in lab B, and Charanjit is in lab A. If we sort these students alphabetically using their names as the key, then it is very unlikely that they will be grouped nicely into lab sections as well. One of the sorting could be Aman is in lab B, Charanjit is in lab A, Dravid lab A, Eric lab B, and Kusum lab A. So, we might like to sort again using the lab section as a key, so that we have all the students in the lab section A together, all the students in lab section B together, and so on. If we now do that, we might end up with this: Kusum lab A, Charanjit lab A, Dravid lab A, Eric lab B, Aman lab B. And of course, we would have liked the students in lab section A to be still in alphabetical order, as well as those in lab section B to be in alphabetical order, but this did not happen. The reason it did not do so was that the sort we used the second time around was not stable. If we had used a stable sort, then we would have obtained this instead: Charanjit lab A, Dravid lab A, Kusum lab A, Aman lab B, Eric lab B. Among simple sorting algorithms, bubble sort and insertion sort are stable, while among the complex algorithms, merge sort is stable. Memory requirements. The amount of extra memory required by a sorting algorithm is also an important consideration. In-place sorting algorithms such as bubble sort and selection sort are the most memory efficient, since they practically require no additional memory. Linked list representations require an additional n words of memory for a list of pointers. Still, other algorithms such as merge sort require sufficient memory for another copy of the input array. These are the most inefficient in terms of memory usage. Adaptability. This is the ability of the algorithm to take a sorted or a partial sorted array and be able to sort it sooner than if it was not pre-sorted. This is often a big deal since it can exponentially save one's time. If we add an element to a sorted array, then the time to sort the array should be much lesser than sorting the complete array if the algorithm is adaptive. Algorithms such as insertion sort, which take care of such cases, are known to be adaptive. Evaluation criteria for sorting algorithms. From time to time, people ask the ageless question, which sorting algorithm is the best? This question does not have an easy or unambiguous answer. There is no single best sorting algorithm for all the data. Various algorithms have their own strengths and weaknesses. The speed of sorting can depend quite heavily on the environment where the sorting is done, the type of items that are being sorted, and the distribution of these items. For example, sorting a database which is so big that it cannot fit into memory all at once is quite different from sorting an array of 100 integers. Not only will the implementation of the algorithm be quite different naturally, but it may even be possible that the same algorithm which is fast in one case is slow in the other. The real performance of the algorithm depends on the system we are coding for, the amount of data, the characteristics of the data, and so on. We also need to consider ease and compactness of coding. As an example, the running times of some of the 6 most commonly used algorithms, bubble sort, selection sort, insertion sort, quick sort, heap sort, and merge sort are shown here. We can see merge sort and heap sort perform quite well on average and do not give bad results even in the worst case. However, for each situation, both these algorithms are outperformed by other algorithms. Bubble sort and insertion sorts outperform merge sort and heap sort when the array is already sorted, and quick sort outperforms when the array is randomly sorted. However, the pitfall is that quick sort performs bad in the worst case, so that it can be quite a risky alternative. We conducted experiments to compare the performance of these commonly used algorithms. Random set of integers of various sizes were used in the experiments. For each algorithm, its running time is shown in seconds up to 3 decimal places. As can be seen, for smaller data sets containing up to 10,000 items, there is not much significant difference in the running times, as all the algorithms take less than 1 second to sort the numbers. But when we increase the size to say 1 million, we find that quick sort, heap sort, and merge sort still take lesser than 1 second, while bubble sort takes 3042 seconds, selection sort takes 2056 seconds, and insertion sort takes 1093 seconds. When the size is increased to 10 million, we see that quick sort, heap sort, and merge sort still take lesser than 5 seconds, but the running time for insertion sort dramatically jumped to more than 31 hours. Bubble sort and selection sort were expected to take even more than 31 hours, and we did not conduct experiments on them. Thus, we can see that for larger set of values, these slow algorithms are practically infeasible to use. Thus, to decide the most appropriate sorting algorithm, we should keep following points in mind. Analyze the problem carefully before deciding the sorting algorithm. Often for small arrays or arrays that are already sorted or almost sorted, insertion sorting will do the job and even perform better than a more complex algorithm. If you care about memory, avoid merge sort, since it basically uses loads of temporary arrays that will be easily overflowing your memory. Even if quick sort has a order n square worst case is often rare, and quick sort will perform much better than merge sort or heap sort on average, since the constants hidden in the big O notation are actually much smaller. Thus, if worst case is an issue and you want to play safe, then go in for merge sort or heap sort, else choose quick sort. Conclusion. With this, we come to end of today's lecture. Today, we discussed the various direct and indirect applications of sorting algorithms, their classification as well as their performance and evaluation criteria. In the next lectures, some of these commonly used sorting algorithms such as bubble sort, selection sort, insertion sort and merge sort will be discussed in more detail. Thanking you.